This module of climate change in Alberta will focus on some basic statistical concepts that will provide the foundation for understanding how climate has changed in the region over the last 100 years, and for assessing the magnitude of the changes in climate that are anticipated this century. Specifically, I'm going to focus on the difference between trend and variability. When considering climate data over time, it is a common mistake to focus too much on the variability and miss the underlying trend in the data, and it's the underlying trend in the data that we really should be focused on. In addition, we'll go over the concept of a normal distribution of data, or the bell curve, because we will use this to analyze Alberta climate data. Lastly, I'll go over some approaches for analyzing the variability in a data set, such as the mean and standard deviation, as these will also help with interpreting the Alberta data. I'm going to start off with a brief video which I believe does a great job of demonstrating the difference between trend and variability. In many complex systems, it's really hard to see what's going on if you're focused in too closely on the details. And what you need to do is to take a step back and get a broader view. And in this case, when we do that, we can see that what we're looking at is a man out walking his dog. Now, in order to determine where the dog and the owner will be in the future, we can forget about the dog and we should be focusing on the owner, because the dog is following his nose. He's running up and down in leaps and bounds. But we intuitively understand that the owner is going to be about here in 10 seconds, even though the dog right now is headed in the opposite direction. And we understand that because we know that it's the owner who determines where the dog and the owner will be in the future beyond a few dog bounds. Now, this owner may stop and decide to head off in another direction, but as is the case with climate, we expect that the owner will continue in more or less the same direction in the future. And the analogy here is that the owner is the climate, the dog is the weather, or the owner is the trend and the dog is the variability around that trend. Here we're looking at some real data. This is mean annual temperature over the last century in the province of Alberta. And the first thing that should jump out at you is it's a very noisy system. There's a lot of spikes or variability in the data, or the dog bounding all over the place. And I think it's in our DNA to focus on this variability. We like to talk about how warm it was last summer or how cold it was 3 years ago. But that misses the point. When we're thinking about climate change, it's really important that we're focused on the long-term, multi-decadal to century scale trend that underlies that variability. Now I'm going to go through the concept of a normal distribution or bell curve. And this is important because we'll be fitting a normal distribution to some of the Edmonton climate data a little bit later on. When I was a kid, most of the exams that I took were graded on a bell curve. And the way that works is if you had 100 kids taking an exam, about, let's say, 24 would get C+, maybe 30 Bs, 21 B pluses, 18 As, 1 genius, and a few kids that didn't do so well on the exam. And the way this works is that most of the exam scores fall around the average. That's where you have most of the results, and you have a few outliers on the high end and the low end of the test results. Now, the same idea applies to climate data. And in this case, we're looking at a hypothetical bell curve of mean annual temperature. And you can see that most of the years where the bell curve is highest fall around the average mean annual temperature. And there's a few cold outliers and a few hot outliers. Now, if we increase the heat in the system, then the bell curve slides over to the right towards the hotter end of the scale. When that happens, you end up with a new climate that has less cold weather that people can recall from the historical climate, but it has more hot weather and more record hot weather. And it's this record hot weather that's off the tail of the historical climate bell curve that's of concern, because most built and natural systems are designed for or adapted to climatic conditions underneath the historical climate bell curve. And it's climatic conditions that are off the tail of the historical climate bell curve that often cause problems. Now, that's not the only thing that can change. The variability can increase. And if that happens, you have fewer years around the average and more hot and more cold and more extreme hot and extreme cold weather, but in equal proportions. Now here's what happens when you do both. You've increased the variability by flattening out the curve. There are fewer years around the average and more extreme hot and cold years. And now you shift it over to the right. Now we have a new climate that still has some of the cold weather that people remember from the historical climate, but it has much more hot weather and much more record hot weather. And again, it's this portion of the curve that's beyond the tail of the historic bell curve that can cause big problems. Here we're looking at some real data, and this is Northern Hemisphere land summer temperature during the 1951 to 1980 base period, and this data has been provided by NASA. And you can see that the data forms a pretty good bell curve. About a third of the years were cold summers, those are in blue. About a third were normal summers, those are in gray in the middle. And about a third were hot summers, those are in red on the right. And you can see that there were very few extremely cold summers and extremely hot summers that are on the tails of the bell curve. Now, as we move forward in time through the decades, here we're looking at 1983 to 1993, 1994 to 2004, and 2005 to 2015. You can see that the bell curve has very clearly shifted towards the warmer side of the axis. And there's some indication that the bell curve may have flattened out a bit and changed shape. But the important piece is that in recent decades, northern hemisphere land summer temperatures have definitely been warming up. And you recall during the base period, about a third of the years were hot summers with very few extremely hot summers. And during this last decade, 2005 to 2015, about 80% of the summers were hot and extremely hot. And again, I would like to emphasize that it's when you get off the tail of the historic bell curve that you often run into trouble. And during that last decade, 2005 to 2015, about 15% of the summers were in that category of extremely hot or off the tail of the historic bell curve. Now we're going to look at the bell curve in a little bit more detail and talk about a couple of basic statistical concepts. And if you're looking at a climate element such as mean annual temperature, for example, if you take the average of all your values during a given period, you'll come up with the mean. And if the bell curve is a good fit to the data, then the mean should roughly divide the bell curve into two symmetrical halves. With a normal distribution, or a bell curve, you'll find that about 68% of the data should fall within one standard deviation of the mean on either side. About 95% of the data should fall within two standard deviations of the mean, and almost all, or 97.7% of the data should fall within three standard deviations of the mean. And there would be very little, about a third of a percent, that would fall outside of this range. Looking at this a little differently, we see that about 34% of the data should fall within one standard deviation on either side of the mean. About 13.6% of the data should fall between 1 and 2 standard deviations on either side of the mean, and about 2.1% of the data should fall between 2 and 3 standard deviations on either side of the mean. And only about 0.13% of the data should fall outside of this range on either end of the bell curve. This concludes Module 1 of Climate Change in Alberta, Trends and Variability.